I'll record here. So last class, we talked about inverse trig functions. So just a quick refresher, right? So that we're kind of, we did a bunch of these problems last time. Let me add in here my unit circle so that... Okay, so last class we were answering things that kind of looked like this, like find the exact value of A, the cosine inverse of minus root 2 over 2. So remember what this is saying. So what we said last class, we set it equal to like theta. You could set it equal to a question mark. You could set it equal to whatever you want. But we said this is, if I think about this, so when we're dealing with the inverse cosine, we're dealing with an angle. So the answer is always going to be an angle. And so really what we're looking for is when is the cosine of theta equal to minus root 2 over 2. And so remember the way that we did this was we looked in the unit circle. Remember the inverse cosine is defined in the first quadrant and the second quadrant. So we looked just in the first and the second quadrant, and we're trying to find when is, remember cosine is the x value, so when is the x value equal to minus root 2 over 2? So all these x values are positive, here they're negative, and here is where it's equal to that minus root 2 over 2. So the answer to this would be 3 pi over 4, right? So in this case, theta is going to be 3 pi over 4, and that 3 pi over 4 was your answer. Questions about that problem? Remember that -1 is just notation. It's standing for the inverse. It's not saying 1 over cosine. Okay, then we also did a couple, so maybe something like the inverse tangent of, say, minus root 3. So same deal, right? We set it equal to theta, and we're looking for when is the tangent of theta equal to minus square root of 3. And so the tangent of theta is going to be equal to minus square root of 3. So remember, tangent, when we're dealing with inverse tangent or inverse sine, we're dealing in the first and the fourth quadrant. And then, so the first thing I'm looking for is when is the tangent equal to minus square root of 3. So remember, tangent is going to be y over x. So if I looked at this point here, if I took the y value, minus root 3 over 2, divided by the x value, 1/2, that would really be minus root 3 over 2 times 2 over 1. So the 2's would cancel. So that would give us minus root 3. So it's there at 5 pi over 3, right? But does anybody remember what was special about the ones we found in the fourth quadrant? What did we have to do with these? Yeah, so we had to turn it into, we had to think of it rather than an angle that starts and goes all the way around this way to 5 pi over 3. We instead want to think about it as an angle that goes this way, that is negative, that's sweeping in the negative direction. And so we talked about how 5 pi over 3 would be the same as minus pi over 3. So this answer here is going to be minus pi over 3. This spoke, the 5 pi over 3, that's the same as minus pi over 3. The 7 pi over 4 is the same as minus pi over 4. The 11 pi over 6 is the same as minus pi over 6. And the 3 pi, the 3 pi over 2 is the same as minus pi over 2. So those are what those 4 negative ones kind of come out to be. Questions about that? No. Okay. So that was kind of like the basic stuff that we did. So what we're going to do today is we're still going to work with inverse functions, but we're kind of going to step it up a bit. We're going to talk a little bit about some of the properties of inverse functions, and then we're going to do some more problems that use those properties. So we can look at the composition. So the composition of inverse functions. Okay, so the sine of the inverse sine of x. So basically I have some number x. I'm taking the inverse sine of it, and then I take the sine of it. So just like when if you took a number and you took a square root and then you squared it, you would get back to the same number, right? So like if you think about the number 9, if I take the square root of 9, I would get 3, and then if I square 3, I get back to 9. So I get back to where I started. So the same thing happens with when you take a composition of a sine with an inverse sine, or a cosine with an inverse cosine, or a tangent with an inverse tangent, with one little stipulation. So this ends up being just equal to sine. So it's kind of like the sine, or just equal to x. So it's kind of like the sine and the inverse sine canceled each other out, but this only happens for all x in the domain of inverse sine. So if you remember, we talked about how the domain of inverse sine, right? We talked last class about the domain and the ranges of inverse sine, inverse tangent, inverse cosine. So the domain of inverse sine was -1 to 1, right? I can only put in values that are between -1 and 1 because the original sine function only outputs values between -1 and 1. Same thing's going to be true for cosine. So the cosine of the inverse cosine of x is going to just be equal to x, again, for all x in the domain of the inverse cosine. Oops. Which is, again, between -1 and 1. And same thing for tangent. Tangent of the inverse tangent of x is going to be equal to x for all x in the domain of the inverse tangent. And remember, the domain of the inverse tangent was -infinity to infinity. So there, it's okay. You could get anything you want. The same would hold true for the inverse inverse cosecant, inverse secant, but we don't really deal with them. So it's usually just the sine, the cosine, and the tangent that we're dealing with. Questions? You guys are very questionless today. How about we do a couple examples? So, find the value of A, the cosine of the inverse cosine of 1/2. Okay, so what do you think it's going to be? Take a guess. The worst that happens is you're wrong, right? It at least makes me feel like I'm not just teaching to the void. Okay. So Carrie said 1. Somebody said pi over 3. Okay. Any other guesses? pi over 3. Okay, so I think you guys are saying pi over 3 because if you found the inverse cosine of 1/2, this inside part would be pi over 3, right? And that's true. This inside part here would turn out to be pi over 3, and so then you'd be left with the cosine of pi over 3, and the cosine of pi over 3 is what? Yeah, 1/2. So you didn't have to do all that work, though. So the thing is see how I have a cosine, and then I have the inverse cosine? All I have to do is make sure is 1/2 between minus 1 and 1. So is 1/2 between minus 1 and 1? Yeah. So since 1/2 is between minus 1 and 1, all that happens is essentially this cosine and this inverse cosine cancel each other out, and we just get the 1/2. So let's try another one. So what about the sine of the inverse sine of 5 over 6? So what do you think that one's going to end up being? Yeah, so again, right, so 5 over 6 is something that's not on the unit circle, so you actually couldn't, like, do what we did in part A, but it doesn't matter. The thing that's important is 5 over 6. You have to ask yourself the question, is 5 over 6, is that between minus 1 and 1? Oops, we're dealing with sine. Still minus 1 and 1. So is 5 over 6 is some number between negative 1 and positive 1? Yeah, so since it's some number between negative 1 and positive 1, the sine and the inverse sine cancel each other out, and so this just ends up being 5/6. So C, the tangent of the inverse tangent of 0. Take out my sweater here. What do we think that's going to be? Yeah. Again, for the tangent one, you can have any number in there, right? And so if I have tangent and then inverse tangent, they end up canceling each other out. So this ends up just being 0. It would work even if I had like the tangent of the inverse tangent of 100, right? So again, the tangent and the inverse tangent cancel each other out. 100 is in the correct place. It's between minus infinity and infinity. I don't really have to worry so much for tangent. So that is just going to be 100. E, my last one here, is the sine of the inverse sine of 4. So what do we think is going to happen there? Okay, so Leon says 0. Somebody says 1/4. Somebody says not valid, undefined. Okay, so, yeah, so the weird thing is like, good, you guys, nobody just said 4, right? Because it's not just going to cancel each other out, because the problem is that 4 is not between negative 1 and 1, right? So since 4 is not between negative 1 and 1, yeah, this does not exist. There's no solution to this. So this does not exist because 4 is not in negative 1 to 1. And there's a mathematical way to write that it's not in negative 1 to 1 without having to write out all those words. And we're going to use that. So the way mathematically to write that would be to say 4, and then this little E symbol here, like a curly kind of E, that means is a member of, is, in. And so we're saying it's not. So 4 is not in the interval from 1 to 1. So mathematically, using symbols, that 4 is not in 1 to 1. That's how you would write 4 is not in the interval from 1 to 1. So giving undefined, does not exist, no solution, any of those works. questions? It's not too terrible. I actually think chapter 5, well, this is chapter 4 still, so section 4.7, then we're going to do chapter 5. A lot of chapter 5 is not actually that bad. So, yeah, so they're easy to overthink. Now, they are going to get a little bit more complex here in a couple minutes, but so far it's not too bad. All right. So somebody asked if I could re-explain B. Okay, so the thing that we want to notice in question B is, so I have a sine and then I have the inverse sine. So these two things are going to cancel each other out, and I'm just going to be left with 5, 6, provided 5, 6 has to be some number between -1 and 1. So if you took 5 and divided it by 6, you're going to get some number between -1 and 1. Let me divide it. I don't know what it is off the top of my head. So 5 divided by 6 is 0.833. 3, it repeats. So 0.83 is a number that is between -1 and 1. So since 5 over 6 is some number between -1 and 1, the sine and the inverse sine essentially cancel each other out, and I'm just left with the 5, 6. The reason it cancels each other out, it's the same thing as if you had like this. If you had an x squared and then you took the square root and the squared would cancel each other out, and you'd just be left with the x. So you're just left with what you started with. It's kind of like what I said. Like if I took 3 and I squared it, and then I took the square root of it. So 3 squared is 9, so this would be the square root of 9, which would just be 3, which is what I started with. So same thing, I'm starting with 5, 6. I'm taking the inverse sine of 5, 6. And then I'm taking the sine of 5, 6. So the inverse sine and the sine undo each other. They kind of like wipe each other out. And I'm just left with the thing I started with. The only caveat to that is that the thing I started with has to be some number between -1 and 1. Does that help? No problem. Other questions before we go on? No. Okay, so this way we did the inverse sine, the inverse functions on the inside, right? So like inverse sine on the inside, inverse cosine on the inside, inverse tangent on the inside, and then we did the sine, the cosine, the tangent on the outside. We could flip it and do the inverse function on the outside and the sine or the cosine or the tangent on the inside. Just like I could, in my example here, I squared 3 first and then took the square root. I could flip-flop that. I could take the square root first and then square it. So that's what we're going to do on the next slide. Okay, so let me write this stuff down. So oops, go back to black pencil here. So this inverse sine of the sine of x is going to turn out to be x. Provided, right, so as long as x is in, so remember when we're dealing with the inverse, sure, yeah, I can go back so that you can still copy stuff. Let me know when you're ready. No problem. Okay, so the inverse sine of the sine of x is equal to x as long as x, so remember the inverse sine was defined in which two quadrants? So we talked about this. Yeah, so 1 and 4, right? Last class we talked about how the inverse sine is defined in quadrants 1 and 4. So as long as x is in quadrant 1 or quadrant 4, but remember when we're in quadrant 4, it has to be written as a negative angle, right? So as a negative angle. So they're going to wipe each other out. They're going to cancel each other out as long as the thing we started with is something in quadrant 1 or in quadrant 4 and we can write it, and it's written as a negative angle. Otherwise, we're going to have to do some work on these problems. The inverse cosine of the cosine of x is going to be equal to x as long as x is in quadrant 1 or quadrant 2, because remember that's where the inverse cosine was defined, in quadrant 1 and quadrant 2. And the inverse tangent of the tangent of x is just going to be x as long as x is in quadrant 1 or quadrant 4. And again, in quadrant 4, it has to be as a negative angle. Right? So those are the quadrants we're looking for in these problems. Okay, so let's try a couple of these. So, for example, the cosine inverse of the cosine of 2 pi over 3. So, I have an inverse cosine and cosine, so they're going to cancel each other out, just like we were doing on the last page. But we have to make sure. So 2 pi over 3, what quadrant is 2 pi over 3 in? Yeah, so 2 pi over 3 is in quadrant 2. And so that's correct, right? We needed the inverse cosine here. It has to be in quadrants 1 or quadrants 2. 2 pi over 3 is in quadrant 2, right? So this is just equal to 2 pi over 3, since 2 pi over 3 is in quadrant 2. B, the inverse sine of the sine of minus pi over 4. So what would that end up being? It's just going to end up being minus pi over 4. So again, the inverse sine and the sine are going to cancel each other out. Minus pi over 4 is in quadrant 4, and it's written as a negative, so that works. So since minus pi over 4 is in quadrant 4. Sure.
So, would it be possible to put 7 pi over 4 as the as an answer, or no?
No. So even though minus pi over 4 is equivalent to 7 pi over 4, remember when we're dealing with, we talked about this last class, when we're dealing with the inverse trig functions, all the angles in quadrant 4 we have to write as a negative. So you can't write it as 7 pi over 4. If it was 7 pi, if this here was a 7 pi over 4, like that's a good example. Like let's say your problem was the inverse sine of the sine of 7 pi over 4, you couldn't actually just cancel them out, because 7 pi over 4, while it's in quadrant 4, it's not written as a negative. So this one we would have to think of as, oh, this is the inverse sine, so the sine of 7 pi over 4 is going to be minus root 2 over 2. And then we have to figure out what's the inverse sine of minus root 2 over 2. The inverse sine of minus root 2 over 2 is, it's in quadrant 4. It is at that 7 pi over 4 place, but we have to write it as a negative, so it's minus pi over 4. Does that help?
Yes.
Other questions? Okay, let's look at another one here. What about the inverse cosine of the cosine of pi over 7. So pi over 7 is not on the unit circle, right? So when I write angles like this, people get like kind of like weirded out a little bit because they're like, it's not on the unit circle. I have no idea where pi over 7 is. So this is where we have to think about the unit circle for a minute. So here, let me put my unit circle back up here. Okay. So on the unit circle, here's pi over 2, right? Here's pi over 3, pi over 4, pi over 6. Pi over 7 is not listed on here, but pi over 7 would be down here below pi over 6, right? I mean, you could have pi over 32 if you want. It's going to be much lower. It's going to be tinier. But all of those values are okay. And so pi over 7 exists in quadrant 1, right? And as long as we have for the cosine, as long as you're in quadrant 1 or quadrant 2, that's okay. So this is actually just equal to pi over 7 because pi over 7 is in quadrant 1. Right? So, if you look at these, right, like I have pi over 2, they're getting smaller. Pi over 2, pi over 3, pi over 4, pi over 6, and then that smaller one, which is pi over 7. Questions on that guy? No. Okay. I have some more here, but we're going to go to the next page. So it's still kind of similar to what we were doing. It's still working with inverse functions. So determine the following. Okay, so the first one is the tangent. I should say, determine the following. I should put your answer will be an expression of x. Okay, tangent of the cosine inverse of 3 over x. Okay, so this problem looks a little different, right? So I have two trig functions that don't match up. And so we usually know what to do with them because we just figure out what the inside is. But here, my inside isn't giving me some actual number. It's giving me 3 over x. And so what we're going to do with these, so when we have these variables x, is we're actually going to go way back to when we first started trig and think of these as a triangle. So if we think about this inside stuff here, this is saying that the cosine inverse of 3 over x, that's the same as saying theta, right? It turns out to be some angle. So anytime we do an inverse trig function, it always ends up giving us an angle. So I'm looking for the inverse cosine of 3 over x. And so it's going to give us some answer that is some angle theta. And this is the same. I can rewrite this as saying the cosine of theta is equal to 3 over x. So basically all I've done is I let the inside stuff be equal to theta. So what I really am looking for now is what is the tangent of theta, because I've just basically replaced all of the inside stuff, that cosine inverse of 3 over x, with a theta. So really in the end, I'm just trying to find the tangent of theta. Now I haven't told us how we're going to find that yet, but does questions about anything I wrote up there so far? Okay, so from this pink part here, we have the cosine of theta equals 3 over x. So we need to think about, how do I make a, like, how would I figure this out? So we want to go way back. So when we were talking about a triangle, cosine was what over what? Okay, so it was something over the hypotenuse. Okay, so when we talked about on the unit circle, we did talk about it as being x over r. But before we even talked about the unit circle, we talked about it in terms of a triangle. And in terms of a triangle, right, the triangle theta, it's the opposite, or not the opposite, the adjacent over the hypotenuse. And so the adjacent here, so if we think about it, what we're saying here is that 3 is the adjacent part and x is the hypotenuse. So when I go to label this triangle, 3 is the adjacent, x is the hypotenuse. And then what would I use to find the missing side? Like if I have 2 out of the 3 sides of a right triangle. Yeah, I use the Pythagorean Theorem. So Pythagorean Theorem says a squared plus b squared equals c squared. So 3 squared plus b squared equals x squared. So 9 plus b squared equals x squared. So b squared is going to be x squared minus 9. So b is going to be the square root of x squared minus 9. So this side here is the square root of x squared minus 9. So these problems are a little weird because we're just dealing with answers and stuff like that that are going to end up having these x's in them. But that's okay. So now I have a triangle, and now if I go back, I'm just looking to figure out what's the tangent of that triangle. So the tangent would be the opposite side, square root of x squared minus 9, over the adjacent side, which is 3. Questions? So I took the stuff that's on the inside, I set it equal to theta, I rewrote it, I used that to help me make a triangle, find the missing side, and then I went back to the beginning to look at what trig function I was looking for that triangle. And I have another one that we're going to do, but before we do my next example, I just thought I want to make sure people don't have questions on this one.
So the answer is square root x squared minus 9 over 3?
Yeah. So the answer in this case is not just some like one little number. The answer in this the answer in this case is that square root of x squared minus 9 over 3. Yep.
But wouldn't the square root cancel with the square?
Okay, that's a good question. So this is where I wish I could just cover something with my hand. If you didn't have this minus 9, if you just had the square root of x squared, then the square root and the square would cancel each other. But you can't distribute the square root to each of these pieces. So in this case, you can't actually simplify this anymore. It just has to stay as x squared minus 9. Does that make sense?
Yeah, so if it's an expression, I can't simplify.
Yep, if it's an expression, you can't distribute that square root to make parts of it nicer. Other questions? No? Okay, should we try another one? So B, the sine of the inverse cosine of x. So again, what I'm doing is I'm letting all the stuff inside here be equal to theta, right? So in the end, I'm really going to just be looking for the sine of theta. And that part that I let be equal to, that's saying that the cosine inverse of x is equal to theta. Or I could rewrite this to say that the cosine of theta equals x. And so from that, I want to draw a triangle. So here's my theta. And again, cosine, we just said, was adjacent over the hypotenuse. And you might go, well, there's no bottom, right? Like all I have is an x. So how do I know what is what? So remember, you can always put something over 1. So you can think of this as x over 1. So the adjacent would be x and the hypotenuse would be 1. And then, if I use Pythagorean Theorem, right, so a squared plus b squared equals c squared. So x squared plus b squared equals 1 squared. So x squared plus b squared equals 1. So b squared is going to be 1 minus x squared. So b is going to be the square root of 1 minus x squared. So that's what's going to go on this side, square root of 1 minus x squared. And so now we're looking for the sine, and so the sine would be what? The opposite over the hypotenuse, right? So the opposite, square root of 1 minus x squared, all over the hypotenuse, which is 1. But I don't really have to write divided by 1, right? So this is just going to end up being the square root of 1 minus x squared. Questions. So a little weird. Well, I'm waiting to see if someone has any questions. If you have to go on and take Calc 2, so you use this idea a bunch in Calc 2 in one of the techniques for integration. So I actually am teaching Calc 2 this semester, and so we actually just did this probably about 2 weeks ago in my Calc 2 class. We used this as part of a problem. So it does come in handy. So Calc 2 is Math 182. So 181 is Calc 1. So after this class would be Calc 1. And then if you have to take another calculus after that, it would be Calc 2. So this concept comes back if you have to take Calc 2. Other questions? I am not supposed to teach Calc 1 next semester right now, the way it's scheduled. Sorry. But I could look up who, if people have to take Calc 1, and you want some recommendations, you can always send me an email, and I can look up who's teaching Calc 1 in the fall. So I have one other problem here. So what about the cosine of the tangent inverse of 3/4? So this one doesn't have an x in it, but the process is the exact same thing as what we were doing with the x's. So again, I want to think of this stuff in here as being equal to theta. So in the end, I'm really looking for the cosine of theta. And so that middle stuff being equal to theta is really saying that the tangent inverse of 3/4 equals theta, or the tangent of theta equals 3/4. And so if I draw this, right, tangent is opposite 3 over adjacent 4. And then I can use Pythagorean Theorem to find that missing side. So a squared plus b squared equals c squared. So 4 squared plus 3 squared equals c squared. So 16 and 9 is 25. So 25 is equal to c squared, or c equals 5. So this side's going to be 5. And then, yeah, as Carrie said, it's going to turn out to just be 4/5, because we're looking for the adjacent, which is 4, over the hypotenuse, which is 5. So it's kind of nice when there's numbers, right, instead of just x's. But the idea is you can use this now for numbers when you have values that are not nice things that show up on the unit circle. Questions? Okay, and I lied. I thought this was the last example, but I do have one more, but then that's it. So, I know, my 2 pages were stuck together. I was like, oh, that's it. And then I was like, oh, no, it's not. So, last one. So, evaluates the sine of the inverse sine of x plus the inverse cosine of y. Oh, wait a minute. Yeah. Never mind. I don't know how this ended up on the wrong... It's in the wrong section of notes because we don't know how to do this yet. I mean, I know how to do this, but you guys don't know how to do this. Because it uses an identity that we don't know yet. So, scratch that. To be done much later. In a few sections later. Sorry. Okay, so, questions. At least I keep it entertaining, right? That's the... Yeah. Okay, so I know I let you guys go early last class, and like it's not a habit. It's not going to happen very often throughout the semester, but I am going to let you go early today, because that is the end of section 4.7, and I know 4.7 takes a little bit of time to wrap your head around, so rather than do other, like go on to section 5.1, I like to kind of give 4.7 its time. So we will be doing section 5.1 next class, and then potentially, depending how fast we get through 5.1, we might start some of the other stuff for the next class. But then we're gonna kind of keep going on from there. So yeah. So the only homework that you have due this week, like, so I finished all the stuff for the homework for this week. The only stuff on the homework that's due this week is 4.7. The stuff from section 5.1 and then the other sections will come up in the next set of homeworks. So if you don't have any questions, you're free to go. If anybody has questions and wants to hang around and ask me more questions, that's fine too. I'm more than happy to answer any more questions.